This is lesson 632. We're going to start learning about functions. Functions are a special sort of a relationship, and this first idea here is presented right here. And this is an important deal. We're going to learn how to identify and represent patterns that describe linear and nonlinear functions. And in general, a function is a relationship. And a relationship is anytime you have a pair of values of input and output values. But a function is a relationship that pairs each input value with exactly one output value. So if you look at these groups, the input values tables here, in this one, 1 goes with 2, 3 goes with 4, 5 goes with 4, 2 goes with -1. There's one line going from each input value to each output value. That is a function. So that's a function. The second one, though, notice that 1 has 2 output values associated with it. So there's 2 arrows going from 1 to the output. When that happens, when you have more than one output for a single input, then that is not a function. So we want to cross out that. And the last one we'll check too. Notice there's 1 arrow from -1, 1 arrow from -2, 1 arrow from 1, and 1 arrow from 2. That is a function. So this is a function. Let me just give you a couple last examples, a couple more examples. Let's say I have this for my input, and my output I have this. Let's say I have 1, 2, 3, and 4 for all my inputs, and I only have one number for my output, 5. So I'm going to pair 1 with 5, 2 with 5, 3 with 5, and 4 with 5. But notice there's just one line from each input to the output. That is a function. But now if I add the opposite of that, let's say I had only 5 for my input, but for my output I had 4 different values. And this 5 is paired with each of these numbers as outputs. That is not a function, because 5 is paired. 5 as an input is paired with more than one output. So to be a function, each input value can only have one output value. All right, we're going to use this idea to help represent functions. This is a function machine. The input has a couple of names. It's the independent variable, x value, input. The output is a y value, or it's the dependent variable. And just as a quick review of independent and dependent, an independent variable is a variable whose value determines the value of another variable, called the dependent variable. So the independent variable is usually x, and the dependent variable is y. And the independent variable is the input, the dependent variable is the output. So using your vocabulary, write I if the first value is independent of the second value, write D if the first value is dependent on the second value. Go ahead and pause here, and then you can check back and see if you did it right. Okay, here's the answers. All right, representing a geometric relationship. All right, in this diagram, notice that the figures keep getting bigger, and they actually are getting bigger in a pattern. And just to help myself out here, I'm going to put the figure number here and the number of squares here. And so in figure 1, I can count the squares. There is 5 of them. In figure 2, I can count the squares, and there's 9. In figure 3, I'm going to count the squares, and there is 13. And you might notice that the number of squares keeps going up by a constant amount. So there's a constant difference here. And it kind of makes sense, because just think about this. Let's say I start with one little square. That could be considered figure 0. Notice that I added a group of 4 around that square. And then next time I added a group of 4 around that, and the next time I added a group of 4 around that. So each time I'm adding 4, so I'm going to think the next figure as 13 plus 4 or 17. All right? So if we think about how many more squares we're adding each time, I can just take that number. So I'm adding 4 to figure 0 one time here, so plus 4, then plus 4 again here, and then plus 4 again here, and I keep adding 4. Well, continuous addition is the same as multiplying by 4. So what I can do is just say, well, if I multiply my figure number by 4, since I'm adding 4, you might notice that that total 4 is 1 less than this total 5. And that's true for each one of these. So my relationship is, if I let my figure number be x and my number of squares be y, y is equal to 4 times whatever figure I have plus 1 more. And we can see from that equation that that's a linear function. All right, this table shows the amount of water in a tank after it says describe the relationship using words in an equation. So go ahead and study those values in that table and see if you can't describe that, or at least think about what it's going to be, and you could pause here and check them. So you probably discovered that there's a constant difference in both the x and the y values, and the difference is 12. So we keep subtracting, going down by 12. And since there's a common difference of 12, we can represent this with a linear equation. And it is a function because each output value is paired with exactly one input value. So we're starting with 440 gallons and the water is decreasing by 12 gallons per minute. The equation is y equals negative 12 plus 440. All right. So look at this next problem. Does the graph right represent a linear function? Explain. This is a relation because it's a pairing of input and output values. This is a function because it's a relationship that pairs each input value with exactly one output value. And it's a linear function. A linear function is a graph whose graph is a line or part of a line. That's the part we don't have here. This isn't a line, this is a curve. So the answer is no, it's not a linear function because the graph is not a line. All right? Okay, for each table, determine whether the relationship is a linear function, then represent the relationship using words, an equation, and a graph. So I'll just do one of these and we'll do the other two in class. But to be a linear function, there has to be a common difference in the x and y values. And so we can see that for this first one, these numbers go up by 1. And if we look closely, you might notice that the y values, the elevation, is going up by 92 each time. We keep adding 92. Since there's a constant difference, this is a linear function. And we can represent this with the equation y being the elevation is 92x plus 1,127. And you, to put this in words, you might say something like the climber starts at 1,127 feet and climbs 92 feet per hour. Then to make a graph, you would just have to choose an appropriate scale for that. Like, I think we'll skip the graphs on these. We've graphed enough linear functions. All right? Sometimes functions are nonlinear, and you will know that. One easy way to tell if they're nonlinear is by making a graph of it. If it's a nonlinear function, you will get something that's not a line or part of a line. So here's some examples of linear functions graph and nonlinear functions graph. So we want to look at, it helps if we make a graph to tell if something is linear or nonlinear. So let's graph this first one here. At 1 inch, there are 2.54 centimeters. That's about right there. At 2 inches, there's 5.08 centimeters, so maybe about right there. At 3 inches, 7.62. And at 4 inches, 10.16. And I'm just going to take a line and see if those look like they are going up at a constant rate. And it seems like they are. Now, one way you might want to double check that is just to find the difference between these values here. And if you did that, I think you would find that you keep adding the same amount, 2.54. So this is a linear function, and because we can tell because the graph is a line. All right, I'm going to let you try it. You can check back with the answers, but go ahead and fill in these problems and make a graph, and then make a decision. Is this a linear or a nonlinear function? I hope you're thinking this is a nonlinear, because we seem to be curving here. And if we don't have a straight line, then it's not a linear function. You can think of a function as a rule that you can apply to the input in order to get to the output. You can describe a nonlinear function with words and/or equation. We have some strategies for finding the equations of linear functions. We don't really have them for nonlinear, so we're just going to have to use our reasoning power to figure this out. And so look at these ordered pairs. Right away we know it's nonlinear because from here to here we're going up by 7. Then we're going up by 19, then we're going up by a heck of a lot more, like 30, 37. So it's definitely nonlinear. And now we just have to see if we can't look at the numbers and try and find a relationship between the x and the y in each of these to come up with an equation. So y equals, and one thing, so we know we're not adding, so we're not going to try that. Let's think about multiplying. Well, if you think about the factors of 8, 8 is 2 times 4, or 2 times 2 times 2, and there it is. 27 is 3 times 3 times 3. 64 is 4 times 4 times 4, and so on. So what we have here is y is equal to the x value multiplied by itself 3 times, or x to the third, and we sometimes say that's x cubed. So this is a cubed function. All right, I think we'll do this one in class. Let's do one more problem and then we'll do the rest in class. When you're graphing a nonlinear function, we know this is nonlinear because it's not written in a recognizable linear form. What we need to do is just find some values. And you probably want to do some positive and negative values just to make sure you get this right. But I'm going to choose these values. And I'm going to start with the easy one, 0. So I'm going to put 0 in for x. So what I'm going to do is 0 squared minus 1, and that's negative 1. 1, if I input 1, then I get 1 squared minus 1. 1 squared is 1 minus 1 is 0. Next one would be 2 squared minus 1, which is 3. And then 3 squared minus 1, which is 8. Negative 1 squared minus 1. Well, actually, that's just negative 1 times negative 1, which is positive 1, so it's really the same as this one, and that's 0. And negative 2 squared minus 1 will be the same as this one, which is 3, and if I follow that pattern, I get that. And then if I graph these, there's negative 3, 8, negative 2, 3, negative 1, 0, 0, negative 1, 1, 0, and so on. And what I end up with is a curve like that. So you need a few ordered pairs to graph a nonlinear function. Go ahead, you try the next one. You should have picked this graph that has the pairs that when you substitute into the function, they are true. That's the end of the video. I'll see you tomorrow.